Hi, everyone. So today we're going to cover chapter 6 in the ebook, which is weathering. And in this case, by weathering, we mean the breakdown of pre-existing rock at both the mechanical and the chemical level. So over there on the left, mechanical weathering processes involve rock breakdown without chemical change. Chemical weathering processes do involve chemical change in the sense that the composition of the rock is actually changing during various chemical weathering processes. So the important information on this slide is just to appreciate what weathering is, namely it's rock breakdown, and then further to understand that we can think of weathering in two broad categories, including mechanical weathering and chemical weathering. So let's start with a brief look at a few different mechanical weathering processes. What you're looking at here is a process called pressure release, and all that's happening is deep-seated rock is eventually exposed at the Earth's surface. In this case, it happens to be deep-seated, intrusive igneous rock. We're looking in the middle diagram at a crystallized magma chamber called a pluton. And at first, that pluton is deep underground, so there's a lot of weight pressing down on that plutonic igneous rock from above. The rock is under high pressure. But through a combination of wearing away the landscape from above, that's erosion, and perhaps tectonic uplift, pushing the landscape skyward from below, eventually the pluton becomes exposed at the Earth's surface. That's part B in the middle diagram. At that point, the pluton is under much less pressure than it was when it was down deep, and so the pluton now expands a little bit. But by now, the rock is hard and brittle, and so when the rock expands a little bit under that reduced pressure, it cracks and breaks up in the process. And what you're seeing is a feature sometimes known as sheeting, and it's often the result of pressure release. And again, all that's happening is the rock is expanding under reduced pressure and breaking up into these slabs or sheets that are more or less parallel to the Earth's surface. There on the right, you're looking at a picture of Half Dome in Yosemite National Park, which is a world-class example of sheeting, which is itself related to pressure release, a mechanical weathering process. Well, depending on the climate, ice wedging, also called frost wedging, can be an important process as well. And very simply put, when water seeps into a crack and freezes, it expands dramatically in volume as a result of turning to ice, something like 10% in volume, in fact. And so if a little bit of liquid water seeps into a crack and then freezes, the expansion of the water as it turns to ice can force the crack apart even more. And particularly when you get repeated cycles of melting and freezing, these repeated cycles can reduce an entire mountainside to rubble in just a few thousand years. That's kind of what you're seeing on the right-hand diagram there. Obviously, ice wedging is going to be important in only certain climates, namely climates where both liquid and solid water can exist depending on the time of day or depending on the season. Well, another mechanical weathering process probably most of us are familiar with is shown here. This is root wedging. And very simply put, it's when roots, plant roots, insinuate themselves into pre-existing cracks in the rock, and then the root grows, forcing apart the crack. So root wedging, like ice wedging, is yet another example of a mechanical weathering process. In coastal areas, salt crystallization can be important. Like here in San Diego, for example. If you were to go to the coast, someplace like Torrey Pines, perhaps, you can imagine that, particularly at high tide, the cliffs there, the coastal rock is going to get a lot of salt spray. Salt spray is just saline water. And when that saline water lands on the rock, it tends to seep into the rock face a little bit, at least a few millimeters. And eventually, when the saline water evaporates, this is when salt crystals form. And the growing salt crystals that are now growing inside the rock are more than enough to wedge grains of rock apart. So that is to say that salt crystallization due to the force of the growing salt crystals as saline water evaporates would be another example of a mechanical weathering process. Again, depending on climate, thermal weathering can be important. Thermal weathering is most important in climates that see a really drastic temperature swing between night and day. And so at night, when it's cold out, the rocks tend to shrink a little bit, they contract. And then during the day, when it gets hot out, the rocks are going to thermally expand a little bit. And kind of like ice wedging, thermal weathering can be important when you have many, many cycles of expansion, contraction going on. But in this case, they're driven by temperature differences rather than water and ice. Okay, on to chemical weathering processes. Oxidation just involves the chemical combination of minerals or mineral components with atmospheric oxygen. And all that you're seeing here in the diagram is simply that the so-called ferromagnesian silicates like biotite, hornblende, etc., are combining with atmospheric oxygen and rusting in the process to produce a new class of minerals known as the oxide minerals. Minerals like limonite and hematite, for example, are common oxide minerals. Obviously, oxidation is going to be most important for the ferromag silicates like biotite because it's these kinds of minerals that are going to be most enriched in iron and magnesium, which are themselves most susceptible to oxidation. Think of dissolution as chemical disintegration in water. So imagine that we have a halite crystal, a salt crystal that we plunge into water on the left-hand diagram, and immediately water molecules begin to attack that crystal and tear it apart at the molecular level. That's what's happening in the right-hand diagram. And so even though the chemistry doesn't really change, the sodium and the chlorine atoms are obviously still present in the water after dissolution. The halite crystal is not. It's the halite crystal that dissolves in water and gets destroyed as a result of dissolution. And to some degree, that tends to happen to all minerals, particularly if the water is even the least bit acidic. And then our final example of a chemical weathering process is hydrolysis. Hydrolysis just refers to the chemical combination with water or its components to produce new minerals. And you can see that long chemical equation there in the middle of the diagram. By no means do you need to memorize this. I just listed it so we can kind of see what's happening during hydrolysis. So we're going to start out on the left there with a K-spar crystal, a crystal of potassium feldspar. And we're going to subject that K-spar crystal to acidic water. And by the way, to a chemist, when you add hydrogen atoms to water, that's what makes the water acidic. So in this case, the K-spar crystal is being exposed to acidic water and it gets destroyed in the process. It's almost like dissolution, except the difference is that in hydrolysis, new minerals get made. It's not just about destroying existing minerals, it's about the synthesis of new minerals, in this case, kaolinite. There on the right side of the chemical equation, kaolinite is a common clay mineral that gets made. It gets produced as a byproduct of hydrolysis in this case. All right, well, what gets made during mechanical and chemical weathering? Another way of asking that is, what are the byproducts of mechanical and chemical weathering? And they're listed right there in front of you. They include both rock fragments and common silicate minerals like quartz and feldspar. And so what's happening here? Imagine a pre-existing rock mass that's being mechanically broken down in the environment into smaller pieces. Some of the pieces contain several different minerals. Those would be rock fragments, ultimately from pre-existing rocks. And if those rock fragments are then in turn broken up even more on a mechanical level, then individual minerals in those rock fragments can be liberated, primarily minerals like quartz and feldspar. As a result of chemical weathering, both oxide minerals and clay minerals get produced. So common oxide minerals would be hematite and limonite. These are both forms of rust, if you will. A common clay mineral, as we talked about in the last slide, is kaolinite. And both oxide minerals and clay minerals get produced as a result of chemical weathering. And then obviously, too, the chemical weathering process liberates chemicals that get added to the water as a result of these chemical weathering processes. So for example, we saw in the last slide that as a result of hydrolysis, potassium ions are liberated and the water becomes a little bit more enriched in dissolved potassium. To some degree, that's true with other stuff as well, including sodium and aluminum, iron, magnesium, etc. This is where the dissolved compounds in water typically come from, namely the chemical weathering of pre-existing rocks. In the bigger picture, this is important because all of these weathering products, rock fragments, oxide minerals, clay minerals, dissolved compounds in solution, all of the stuff is going to become the raw material for sedimentary rock. It turns out, though, that in terms of susceptibility to chemical weathering, not all of the big 8 silicates are created equal. You might remember this diagram on the left-hand side of the page. That's Bowen's reaction series. And you might also remember that up toward the top of the diagram, these are minerals that crystallize at relatively high temperatures, minerals like olivine and calcium-rich plagioclase. And then as you move downward on the diagram, you move into minerals that crystallize at lower and lower temperatures. So that's Bowen's reaction series. In this case, though, we're not going to focus on crystallization temperature. We're going to use that same diagram, namely Bowen's reaction series, to help us understand how different minerals are more or less susceptible to weathering, specifically chemical weathering. And you can see on the diagram that high temperature minerals like olivine and pyroxene and calcium-rich plagioclase are more susceptible to chemical weathering. That just means they're broken down chemically more easily in the environment. And lower temperature minerals like K-spar, muscovite, and quartz, and also clay minerals, I would add, are less susceptible to chemical weathering. That just means that they're going to hang around longer in the environment. They're not going to go away. And again, this is important for sedimentary rocks because it turns out that low stability minerals up toward the top of the diagram aren't really very common in sedimentary rocks precisely because they decompose so rapidly at Earth's surface. So if you have a rock that contains, a whole bunch of minerals, including many of the minerals shown on the diagram, it's the high temperature minerals that go away first. They become destroyed as a result of chemical weathering, and almost by default, you end up with sort of a residue, if you will, of low temperature minerals like feldspars and muscovite and quartz, etc., that are less susceptible to chemical weathering. So that means that in the next chapter, when we look at sedimentary rocks, guess what? We're going to find that many sedimentary rocks are, not surprisingly, going to be enriched in feldspar and quartz. Okay, on to the weathering cycle. All I want you to appreciate by this slide is simply that mechanical and chemical weathering each reinforce the other. And you can study the details on the slide. But another way of thinking of this is that the more that Mother Nature mechanically weathers the rock, the more that rock becomes susceptible to chemical weathering. And vice versa. The more that the rock is chemically weathered, the more susceptible it becomes to mechanical weathering. That is to say, when it comes to mechanical and chemical weathering, each group of processes reinforces the other. Okay, what about the relationship between weathering and climate? I've kind of been alluding to that throughout today's presentation. So it turns out that in general, as temperature increases at the Earth's surface and also as rainfall increases, both conditions are associated with more intense chemical weathering. So you can see there in the diagram that on the x-axis, on the horizontal axis, as we move to the right, we get more and more average annual precipitation. And also as we move upward on the diagram to warmer temperatures, both of those situations are going to be conducive to strong chemical weathering. And guess what? That means that we can say in general that rocks are chemically weathered most intensely in warm, wet environments, generally close to the equator, or at least in the tropics. On the other hand, it's primarily in dry environments where you don't have much water available that mechanical weathering is also going to dominate. And by dry environments, that can also be dry, cold environments. In polar environments where it's really, really cold, too cold for liquid water to exist, believe it or not, in those really cold polar environments where you don't really melt ice very much, it's mechanical weathering that dominates due to the absence of water. Water helps drive chemical reactions, and so that's why it contributes to chemical weathering. If you don't have liquid water, either because your environment is warm and dry or because it's cool and dry, then it's going to be mechanical weathering that tends to dominate. Very quickly, just appreciate from this slide that the ultimate byproduct of weathering is soil. Soil is a whole mixture of different things. You can see there in the slide. It's living and non-living organic matter. It's gases like atmospheric oxygen. It's water. And it's weathered material, both mechanically and chemically weathered rock material. And so this complex mixture is what we call soil. It becomes soil when the mixtures are such that they can support the growth of vegetation. Okay, well, I wanted to just close out this chapter by talking to you a little bit about the relationship between weathering, plate tectonics, and climate. So what you're looking at in the diagram there is a simple plate tectonic diagram. And you'll notice on the left-hand side of the diagram, there's a subduction zone. In the middle of the diagram, there's a divergent plate boundary. And then on the right-hand side of the diagram, there are some mountains. So what happens at both subduction zones and divergent plate boundaries is that CO2 gets added to the atmosphere from volcanoes. We've learned already that that's where most volcanoes occur on planet Earth, either along subduction zones or along divergent plate boundaries. Volcanoes certainly extrude lava and pyroclastic material, as we now know, but they also extrude gases like carbon dioxide. Carbon dioxide is a greenhouse gas, and that just means that it acts like a heat blanket in Earth's atmosphere to trap heat energy that would otherwise bleed out into space, thus cooling the planet. So gases like carbon dioxide and methane and other gases that are coming out of volcanoes, these help keep the climate warm because they add greenhouse gases, heat trapping gases to the Earth's atmosphere. And again, that tends to happen at both subduction zones and divergent boundaries. So where I'm going with this is that plate subduction and plate divergence ultimately help warm the climate. But the opposite also occurs at both subduction and collision zones through chemical weathering, the topic of today's presentation. Here's how that works. So if we imagine a collision zone, for example, as the lithosphere is horizontally shortened and crumpled up and sort of smushed together, as we now know in the course, this happens at two continental plates, and we get big, tall mountains produced as a result, mountains like the Himalaya and the Alps and so forth. And now when that mountain is sitting there, and when rainwater falls through the atmosphere, ultimately landing on the mountain, the water is a little bit acidic. Why is the water typically acidic that's raining down on the world's mountains? It's because as the rainwater is falling down through the atmosphere, it's absorbing carbon dioxide that got added to the atmosphere by volcanoes. And when that carbon dioxide is combined with liquid water, a weak acid known as carbonic acid is produced. And here's the thing. When this slightly acidic water then lands on these mountainous landscapes, the rock is dissolved, particularly if it's silicate rock. And here's the thing, carbon dioxide is consumed, that is, it's used up. So imagine a volcanic arc, imagine tall mountains at a collision zone. In both places, acidic rainwater is falling on the mountains, using up carbon dioxide in the process. Carbon dioxide is destroyed in these plate tectonic environments, and as a result of chemical weathering, this process helps cool the climate. So in the second bullet there, then just to summarize, at both subduction and collision zones, carbon dioxide is removed from the atmosphere as silicate rock chemically weathers via dissolution. This is what cools the climate. So the take-home message here is that it's plate tectonic processes that help control chemical weathering and sort of keep Earth's climate in balance. Okay, everyone, well, I encourage you to go back and review this presentation, and then certainly keep going in the course. Move on to Chapter 7, which is sedimentary rocks.